Okay, so here's what we were talking about last time. We were talking about new kinds of Riemann sums, right? So new kinds of domains, I want to say it as. So for example, maybe this is a domain in the sense that maybe over this set, I might want to add something up, right? I might want to compute the mass distributed on that curve in the xy plane, or I might want to compute the mass distributed on this surface in XYZ space. Chop it up, add it up. Now maybe I'm computing mass, maybe I'm counting ants, so whatever, right? But for whatever reason, I want to do a chop it up, add it up. How would I do that? They're not single variable integrals. They're not double integrals. They're not triple integrals. They're just not our previously discussed kinds of Riemann sums. But they're still sets that I can chop up and pose that I add up. Right? So all I've done in writing this down, for example, is observe that I can chop up this curve into little pieces that have an associated length. Which, if I'm interested in computing mass, I would want to multiply by density, or if I'm computing ants, I'd want to talk about multiply by population of ants per unit length, or whatever, appropriate to the application. And then having done that on each little piece, I would then want to add it up over all the pieces, right? Some sort of an accumulating quantity like mass, ants, right? And then, of course, I'm going to have round-off errors, and the idea of taking a limit is that, well, fingers crossed, hopefully the round-off errors go away. Okay. So it's all the same ideas of all the integrals we've talked about in the past, just a different sort of different context, different details. Likewise here, we get little pieces of area that I would want to multiply by some sort of associated density appropriate to the application. Maybe I'm computing mass, therefore mass per unit area. Maybe I'm computing ants, therefore ants per unit area, whatever. And again, add it up and get rid of the round-off errors. Okay, so we talked about these. Again, we have these new shorthands as well for representing these Riemann sums. We're going to call them integrals. I'm going to call this a scalar line integral. Line, because the domain is, it's a little awkward. We should probably call it a curve integral, but historically everyone calls it a line integral, so I'm on board. Fine. So line integral. I am going to call this a scalar line integral. There is another kind of situation that's going to come up soon. We're not ready to talk about it yet, but there will be another kind of line integral that's fundamentally different from this, way I see it anyway. So scalar is in recognition of the fact that there is a scalar differential and that there is a scalar integrand. The new kind of line integral we'll talk about later will be different. But anyway, that's a foreshadowing. And then likewise, this is a scalar surface integral. Obvious reasons. Okay, so we discussed last time. We're going to do the same thing here that we've done in the past when we've had an undesirable domain. Typically, in the past, what's been undesirable is our domain was all curvy and cornery or awkward and something like that, right? This is just a new kind of awkwardness. It's dimensionally awkward. Now, this is a kind of outside of the world it should be in. This is a two-dimensional domain, but it's not in 2 dimensions. It's in 3 dimensions. So that's awkward. So, as discussed before, we're going to find a way to view them as being images, just like with change of variables. We're going to do a pullback and keep track of the, of course, obvious stretching factor concern, just like with change of variables. And then the result will be an integral that hopefully we can deal with more easily. Okay, so I'm going to start off with curves and line integrals real quick. We're going to switch to surfaces right after this. The book does a thing that I think is, I think it's a little unnatural, but this is my opinion, where the book doesn't even bring up curves and line integrals until after it's already done most of the work on dealing with surface integrals. And I just kind of feel like it's easier to start with low dimension and work your way up to the higher dimension. So I want to at least use curves as a segue to doing surfaces. We will pretty much stick with the book's order. We are going to do surfaces for most of today. But I'm just, again, for segue, sort of for example purposes, I am going to start with curves. So here we are. We have a curve in the XY plane. I want to do a chop it up, add it up on this curve for whatever reason. Therefore, I need to understand that little piece of length. Now, that's a small picture. I don't want my entire picture to take place on something that big, right? It's a teeny tiny little thing. So I'm going to expand this for visual convenience. And again, this is just for visual convenience. So this is, we're magnifying glass, looking at, looking at that same little thing up close. So here's that little piece of curve that we're interested in. I want to compute how long that is. Yeah. And, well, I want to know specifically how long is that, but more to the point, I would like to know by what factor, how does this function, whatever that is, how does that function stretch out a little blue piece of the t-axis of size dt? How much does that stretch out to become this little green piece of the curve ds? All right, so I'm going to compute ds. And then we'll figure out what it is times dt. Okay. All right. So here we are. We want to understand that length. Now, good news, that length is the length of a vector. At least in a differential approximation. Let's see if I can draw a straight line. There we go. And you may recall we've talked about this vector in the past, the vector differential of position along a curve. Way back in chapter 12, we called that dx, right? And it's very natural notation. Remember, differentials mean linear approximations to changes. Well, this is our linear approximation to the change in position x, right? So x was here. Later along the curve, x is here. The actual change in position is that, but my differential estimate of that change in position is not quite the same. It's based on looking at a tangent line, and so it's that tangent dx vector. Anyway, the whole idea of differentials, as you recall, is that it's easier to compute them. Right? So dx is a convenient thing to talk about, a convenient estimate of the actual displacement. Okay, so we want to understand dx. Dx has got easy components to understand. Let's look at the first component of dx. There it is. It's just how much does the first coordinate change? What's our linear estimate of how much x changes as t changes? Well, it's the derivative, right? This is a single variable calculus observation. You change t, correspondingly change x. Those differentials are related by the derivative. Okay. Along those same lines, the second coordinate of the dx vector, well, that's the differential of y, and again, it's an easy single variable calculus problem. There it is. Right? So, knowing dx and dy, those are the coordinates of the dx vector that I'm trying to understand. And so, there's my dx vector. Having written that down, now of course keep in mind what I'm interested in is the length of this little piece of curve. Again, I'm approximating that with the magnitude of the dx vector, so I've got to take the magnitude of that dx vector. And y'all know how to take magnitudes. This is chapter 12 thing, right? It's the square root of the sum of the squares, and you kind of write it all down. Factor out a dt. Remember that the square root of dt squared is dt. What's the absolute value of dt? But dt is positive. There's a whole thing here, right? But anyway, that magnitude calculation is pretty easy to do. And notice my picture's getting a little messy at this point. Let me clean that up. Notice the nice punchline is that I have this thing here, which is, well, its speed. It's the magnitude of the velocity vector. And that is the thing that allows you to compute ds as being a multiple of dt. So speed, the magnitude of the velocity vector, is my stretching factor. Let me sort of circle appropriately then. This ds, the ds that I need to rewrite, it is something times dt, and the stretching factor that you see here is speed. Okay, does everybody see how this calculation went down? By the way, I'm well aware of the fact that you can get this result in a much easier way by saying, look, come on, man, distance equals rate times time. That is that simple little rule that we all learned way back in, I don't know, middle school or something, right? The point to this calculation is not to get the answer. The point to this calculation is to see how we can understand pieces of our domain by way of vectors, how we can compute those vectors by coordinates, and then how we can use algebra to get what we eventually need. Right? So like I said, this is a warm-up problem. This is a segue. We are now going to pretty much set this aside. We're not going to look at scalar line integrals right now. We'll do it later. I want to now take this strategy, though, and apply it now to surfaces. Wait a second. I forgot to make a comment here. Let me come back. Let me come back to the very start of this page. Reminder, our goal is to view this curve as being the image of something nicer. Curves I can think of as being images of intervals on the t-axis. And so there is a function that will do this. And the very quick comment I forgot to make is we've already done this. Viewing curves as images. That's parameterizing the curves. Right, so I just wanted to make that connection real quick. Where we get this x function, that thing whose various derivatives I compute, and yada, 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 that thing is just a parameterization of the curve. Okay. All right. Okay, so moving along to surfaces now. Same kind of a deal. Here's my undesirable surface, undesirable for sort of dimensional reasons. It's a two-dimensional thing in a three-dimensional world. It's not. I can't do a triple integral. I can't do a double integral. It just doesn't really make any sense. If I could find some way to view that as an image of a two-dimensional region in a two-dimensional space, then if I could do a pullback, I mean, an integral on the blue domain is fine. That's a two-dimensional region in a two-dimensional space. It's a double integral. It's early chapter 14. No problem, right? So this sort of a pullback would be super. Question, how do we find such a function? How do we view a surface as being the image of something? This too is called a parameterization. It's just now we call it a parametric surface instead of a parametric curve. But it remains that we're viewing our end result, the thing we're interested in, as an image. How you find this function is another conversation. So that's not something we've seen before. But we will address that question pretty soon, later, in like 15 minutes or something. So for the moment, let's just assume that we have that given, right? And then afterwards, I'll show you some nice techniques for how to find such functions in practice. Okay. Alrighty. So again, I'm interested in understanding a little piece, this time of my surface. I'd like to view that as being somehow a stretched out version of this little piece of the pullback domain. I would like to know by what factor does that get stretched out. No surprise. What I'm going to do is I'm going to compute the area of that little green piece of surface. And I'm going to, with fingers crossed, hope I can view that as something times the area of the little blue piece of surface. Now again, I need to expand. Everything I'm interested in from here on out is contained in these tiny little yellow circles. So let's magnify those just for visual convenience. But don't forget, this is what we're talking about. We have a little piece of pullback domain that is a pullback from the original piece of surface. We want to relate them. Okay. So, for visual convenience, here we are. Here's my green piece of surface. That is a pullback. That is the image of this little piece of pullback domain, this little blue rectangle. The blue rectangle is easy to understand. This is in the UV plane. The width is du. Right? The height is dv. That part's easy. Right? So this area in here is du dv. No problem. To deal with this curved piece of surface, it's curved and stuff, right? And that's awkward. But let me remind you, back up here, this little piece of of this curve was curved too. How do we understand curved things? Well, we approximate them with flat things. And we understand the flat things because they're easier to deal with. Okay, so we're going to do the same thing here. I'm going to try to understand this piece of surface by looking at this parallelogram that approximates that curved piece of surface. Where does this parallelogram come from? Well, I don't think it's too surprising that if I were to take, I'll do it in this color. If I were to take this displacement here, du, in the u direction, that would cause a change that I would linearly estimate by that little arrow. And then likewise, this change would cause a change that I would linearly estimate with that arrow. And this purple parallelogram is just going to be the parallelogram that results from looking at the blue output vector and the red output vector. Right? And so if I can understand this parallelogram, then I can understand, close approximation the piece of surface. Okay, so let's go back to, stylus. That input arrow, this output arrow. How do I understand that output arrow? Well, look, we're going to do something very similar to what we did back here. We understood this output arrow by looking at its coordinates, which were easy, one at a time, easy to understand. That is just a derivative times dt, right? And then likewise for the other coordinate. Here, same deal. It's just that now there are 3 coordinates, and you got to look at them one at a time. Let's look at the first coordinate there of this dark blue vector. That first coordinate says how much does x change per unit change in u. Well, and by the way, notice that v is held constant, so v is not changing at all. So in this discussion of this dark blue vector, I want to know how much x changes as u changes while v is held constant. And that is, again, an old conversation. Partial derivatives crush that, right? The partial derivative of x with respect to u is what you multiply by du to get dx. Similarly, the change in y as u changes and v is held constant. It's another partial derivative problem. And then finally, the change in z as u changes and v is held constant. Another little partial derivative problem. So you just write them down. I mean, it's really the same thing that we did back here. It's just that now there's 3 coordinates instead of 2. Right, so then all together, looking at this vector as a whole, that vector has these coordinates, and there's a common factor of du in all of the coordinates. Notice that we're looking at partials of all of the coordinates of x with respect to u. So really, it's just the xu vector, the u partial of the x vector, the u partial of our parameterization times du. Okay. All right. Now I'm going to leave it as an exercise for y'all. This is a nice exercise to make sure. Oh, whoops! I'm sorry. I didn't mean to do that. Here we go. Let's you guys compute what happens when you change v instead of u. You're going to hold u constant. V is changing. As v changes, that causes this linear approximation of displacement. And how would you compute its coordinates? What do you end up with? And side note, the answer is going to be xv dv. It's what you would guess by analogy, right? So that's good news. But to think about the arguments, think about how, what changes, how would you draw the picture, and persuade yourself that that's true. Okay. All right. So, good deal. We know these 2 vectors at this point. Keep in mind, my goal is to understand this area. This area of this parallelogram. I want to understand the area of that parallelogram because that's how I'm approximating the area of the little piece of surface that that's sitting right underneath it. How do we compute the area of a parallelogram? right? Flashbacks way back to early chapter 12, right? The area of a parallelogram in three-dimensional space. It's the length of the cross product. Right? So I'm going to compute that at literally as the length of the cross product. Area is the length of the cross product. Of course, cross product of these two vectors that we just computed. And so there's your formula. Now, keep in mind, my goal was not just to compute ds by itself. I want to know how is ds a something times du dv, my original pullback, or my pullback area. And notice that these differentials, du will factor right out, dv will factor right out, and you factor those out, and as desired, you get that du dv is something times, du dv times a now identified factor gives you ds, and that stretching factor, there it is, you see it. It's just, it's a weird little formula, but this is, there it is, that's how it worked out. That's the weird little formula that is your stretching factor when you're pulling back our surface integral. Right, so reminder, all of this was about, going back to, way back here, first, at the very start of today, we're trying to compute some sort of chop it up, add it up situation on that surface. I'm computing mass or ants or what have you. And, okay, so I need to know how to pull back this integral. Right? We needed to do a pullback, find the corresponding stretching factor. We were looking at these scalar surface integrals. We just got through computing ds. We've identified the stretching factor. So our surface integral that we were interested in, here it is. Surface integral that we were interested in here. ds is stretching factor times du dv. We just computed that stretching factor. That's what you multiply by du dv to get ds. Just plug it in. And everything else is just plugging in. X is, sorry, my elbow. X is, of course, a function of u and v. Just plug that right on in there. Like every other pullback that we've done, change of variables or different coordinate systems, what have you. Just plug in what the output coordinates are, just directly from the change of variables function. And you've got yourself a new integral. Okay. All right. So that's we're going to see some examples here in a couple of minutes. Real quick, I want to make a notational observation, and that is, it's hard to see this coming, but you have to take my word for it. This vector in here, that vector turns out to be interesting for other reasons, and with applications that are really quite nice. So instead of thinking of our stretching factor as, this formula, magnitude of xu cross xv, I'm going to give this orange vector, I'm going to give it a name. This is the same choice that the book makes. I think it's a perfectly reasonable choice. We're going to call it capital N. It's a nice little shorthand. So we're going to rewrite the stretching factor as magnitude of capital N. If nothing else, like I say, nice shorthand. But again, it's also interesting for different reasons. So just a real quick, why do I care about this capital N vector? Why do I care about xu cross xv? Let's go back to our picture here. Notice that xu, this xu is parallel to the surface. Right, here's my original piece of surface is that. So xu is parallel to the surface. Likewise, xv is parallel to the surface. So their cross product, being as it is perpendicular to each of those two vectors parallel to the surface, that cross product is perpendicular to the surface. It's always orthogonal to the surface. And that's a nice feature. It's geometrically interesting. Perpendicular to the surface. So our N vector is perpendicular to the surface. That's going to end up being part of the reason why we actually care about the vector, and there's more details to discuss. I do want to say one last real quick, about the notation. Notice I'm using capital N. Back in chapter 12, when we were doing lines and planes, we used lowercase n. Who cares? What's the difference? The who cares is that back in chapter 12, we weren't really interested all that much in the length of the normal vector. The normal vector was just any vector. Who cares? What any vector perpendicular to the plane you're interested in, whatever, right? This n is not whatever. This n is a very specific formula. This n is exactly that. It is not just any vector perpendicular to your surface. It's that vector perpendicular to the surface. Right? So do be careful with that. Capital N is a very specific thing. Notice further, capital N depends on what parameterization you choose. It comes from taking specifically your parameterization X, that parameterization, not just whatever parameter, your parameterization X, and doing a certain thing. Take some partial derivatives, take a cross product, right? But it comes out of the parameterization. So it's rigidly defined, and therefore has to be distinguished from the, whatever, any normal vector you feel like. So that's where we're using capital N instead of little n, and anyway, just be careful and heads up about that. Leads to problems later on. Okay, so all this in mind, our stretching factor, we rewrite like this, with that vector having been rewritten like that. And so here's the formula that I want y'all to all memorize, and that is if you want to do a pullback of a surface integral, there it is. And don't forget that capital N is XU cross XV. Okie dokie. So now, before I show you an example, I want to do a callback. Now, another callback. So remember when we did change of variables, and I wrote down the formula for the stretching factor, and I said, look, we got a lot going on right now. Let's talk later about where that formula for the stretching factor and change of variables comes from, and we got a lot to deal with. So let's deal with this other stuff we're dealing with. I never got back to y'all on that, right? Until now. Now is the time that I was referring to. I was foreshadowing. I'm going to show you now how to find the stretching factor for change of variables. In fact, let me rephrase that. I'm going to kind of make a vague outline, and I'm going to let y'all do it. And you can totally do this. We now have all the ideas that we need for y'all to figure out on your own the stretching factor for change of variables. In fact, we kind of already have a picture drawn. It's kind of this picture, kind of, sort of. With one difference, this picture is of a surface that's in space. Just forget about all this 3 coordinate business. Let me just kind of erase these 3 coordinates. We'll just view this as being a picture in 2 dimensions. Right? And we want to compute the area of this little piece of the XY plane. Well, of course, we're going to approximate that little piece of area in the XY plane by this parallelogram. That parallelogram is defined by these vectors that you can write down formulas for. It's just coordinates or partial derivatives appropriately, times a differential. So compute these vectors. It's going to be super analogous to what we did down here, except instead of now there being 3 coordinates, now we're just in the XY plane. There's just 2 coordinates. You can totally write down those vectors. Having written down those vectors, we're now in 2 dimensions. How do you compute an area of a parallelogram in 2 dimensions? It's not a cross product. There is no cross product in 2 dimensions. If you have a parallelogram in 2 dimensions, again, think way back, early chapter 12. Make a matrix, take the determinant. That's the formula for the area of a parallelogram. Write that down, look at the coordinates, factor out, blah, blah, blah. Kind of follow the sort of the algebraic structure of what happens here, and what you will find is that the stretching factor for this situation, so the area stretching factor here, is exactly the formula that we wrote down back in the section on change of variables. So it's very literally a 2-dimensional version of what we just did here, adapted appropriately. It's I think a fantastic exercise. Y'all can totally do that. If you get stuck, you're not sure, ask somebody, come talk to me in office hours. be happy to help you with it, right? But I think it's very valuable for y'all to do that on your own and derive your own stretching factor for change of variables. Okay, so let's see an example. Suppose I have a surface that is parameterized by this function. Notice that's a parameterization, so x and y and z are all functions. I kind of made a mess there, didn't I? X, y, and z are all functions of u and v, as promised. Right back to the picture. X, y, and z are functions of u and v, thus a parameterization. Notice in this first example, I'm giving you the parameterization, explicitly giving it to you. Again, we don't know how to find parameterizations yet. We'll get to that real soon. Bottom of this page coming up. Right, but for the moment, again, just to kind of get our hands dirty, get one done, get a scalar surface integral under our belt. I'm just going to take this as given. So that being given, and specifically the pullback domain is also given. You'll notice. Specifically, we're looking at the image through this function of that range of values of u and v. So we've got a rectangle in the UV plane. And that makes a surface. On that surface, we've got a density given. That's mass per unit area. Given that amount of mass per unit area, distributed non-uniformly, you'll notice, over this area, what's the total mass? Right, how do I compute the mass of this thing? Well, mass is a scalar surface integral. We're taking a surface, we're doing a chop it up, add it up on a surface. That's a scalar surface integral. In order to be able to compute a scalar surface integral, I need to know my stretching factor. So I'm going to have to go back over here, right? And I'm going to have to play this game. I'm going to have to take my parameterization. I'm going to have to compute various partial derivatives. I'm going to have to take the cross product. I'm going to have to compute the magnitude of that cross product. I've got to go through this whole little calculation, but I'm just computing the stretching factor as written there. So here it is. I'm going to go quickly through the tedium, but your parameterization, there's the partial derivatives. Here's the cross product. There's the magnitude. Just a bunch of details, right? Now, reminder, make sure you can do that, right? You got to be able to compute cross products to be able to do this. You got to be able to compute partial derivatives. These were easy. Again, I wanted to have an easy starter example. Make sure you're good at partial derivatives, good at cross products, proficient with magnitudes. There's a little bit of sort of algebra at the end here of, how to rewrite that. I think it's always good form, right? And now that you've got your stretching factor, it's really all over but the shouting. Notice that our ds, per the whole strategy on the previous page, ds is stretching factor times du dv. There's our stretching factor strategy. Right? We got to worry now about the integrand. So our density, density was given. Density is that. Oh, wait a minute. What are x, y, and z? What are x, y, and how do I rewrite x, y, and z in terms of u and v? Don't forget, that's what the parameterization is. The parameterization literally is telling you x, y, and z as functions of u and v. So the way you get rid of those x, y, and z is just plug in. Again, it's right here staring at you in the face. X is that. Right? So that's what happens to x. Y, again, given in the parameterization, so y becomes that, etc. for z. So all I've done in turning that into that, I'll say like in turning that into that, is I've just remembered that, that's x, that's y, that's z. Stick them in there. Yeah, everybody good? Okay. A lot of students mess up on this. A lot of students, we've talked about this before, but I'll be brief. A lot of students are like, well, I'm changing from these variables to those, so I guess, is X U, and maybe Y, I'll just rewrite X, call it U, and maybe Y, I'll just call that V, and then they're never quite sure what Z should be. Right? But anyway, so don't just make something up. You've got the formula right here for what X, Y, and Z are. Okay. And like I say, then it's all over with the shouting. This is a double integral. It's a plain old, good old section 14.3 double integral. Okay. Over a rectangle, by the way. That's nice, right? This is an easy double integral. Okay. All right. So that's how you do scalar surface integrals. Asterisk. How do you parameterize? Where did the parameterization come from? Yeah, we'll get to that in a second. But notice, other than that, scalar surface integrals are highly plug and chug. Okay. How do you get that parameterization? There is no single magic trick for this, but there is a really good trick that works most of the time. Well, it works very often. I'll say very often. Right? Usually. And this is what I like to call the graph parameterization. The big idea is in whatever algebra that you're given, try to write one of the coordinates in terms of the others. If you can write one of the coordinates in terms of the others, then you can almost instantly write down a parameterization. This is my favorite trick for parameterizing, by far. So here's, for example, let's suppose you want to parameterize this plane. How would I parameterize that plane? Well, per the suggestion, I'm going to write one of the coordinates. I'm going to choose Z in terms of the others. Now, the others, we just solved for Z, so I need to rewrite Z in terms of, X and Y. And notice, right? I've rewritten Z in terms of X and Y. So just solve for one of the variables. Having done that, the next step is remarkably convenient. Take these other variables, so X and Y in this case, just define them to be your parameters. Now keep in mind, we're making this parameterization. It's our parameterization. We can do whatever we want in defining this parameterization. And what I suggest that we should want is to make it as easy as possible. So let's just define X and Y to be U and V, and notice that everything else that just kind of works out. If X is U and Y is V, then notice Z kind of has to be that. So it's like I say, it's a really easy two-step process. Solve for one of the variables in terms of the others. Let the others be your parameters, U and V, and celebrate. Right? Here it is. I have X, Y, and Z as functions of two parameters, U and V. I have a parameterization. Isn't that nice? Okay. All right. So please take this trick seriously. I think this is a very valuable tool for parameterizing things. Okay. All right. So here's an example. Suppose I am looking at the upper unit hemisphere. Emphasize, we're talking about the surface, not the solid, right? This is not a half a ball. This is half of a sphere. Sphere is a surface. The upper part, by the way, so just the part where Z is greater than or equal to 0. Okay, how would I parameterize this surface? Well, step 1, can I solve for one of the variables in terms of the others? Now, there's a temptation to look at this and say, yeah, I could solve for any of the three variables. Not really. You'd get a plus minus. So you didn't really solve, for example, for X. You can't solve for X. You can reduce it down to a short list of possibilities, right? But you can't say X equals function. Functions have to have a single value. This is non-negotiable, right? Single value to be a function. So you can't really solve for X. And likewise, you cannot solve for Y, but you can solve for Z. You can solve for Z because being, as we are looking at the upper unit hemisphere, we know Z can't be negative, and so therefore I don't have to say plus minus ambiguities, right? Z is the positive square root. Says so right there. Yeah, everybody good? Geometrically, if you prefer, the vertical line test works just fine. Whereas, if you try to do the x or y equivalent to the vertical line test, you fail. Right? You intersect twice. Okay, all right. So, having done that, notice my parameterization. Let u and v be x and y. Plug that into there. The z, therefore, sort of has to be that. My hands are tied, right? And there's a parameterization. X, y, z. It's a function of two parameters. Everybody see how that worked? Happy? Okay. What's the range of values now? So if we were for example, if we were computing the mass on this hemisphere, what's the corresponding range of what is my pullback domain in the UV plane? Notice that u and v, if I want to know the range of values of u and v, well, after all, u and v are exactly x and y. So to know the range of values of u and v, I really just need to know the range of values of x and y. And in this function, where z is a function of x and y, like this, right? Over what range of values of x and y do I get the surface? Well, it's that range of values of x and y. X and y is that, let's see here, this is a unit hemisphere. So x and y, the range of x and y is the unit disk. So if x and y range over the unit disk, then u and v range over the unit disk. Does that make sense to everybody? Okay. All right. Let me show you another example. Same example. Unit hemisphere, upper unit hemisphere again. And notice that I could solve for a different variable. Instead of solving for z, I could solve for a spherical variable. I could solve for rho. It's real easy to solve for rho because the equation is rho equals 1. Super easy to solve for rho even. And having that, notice again, everything kind of falls into place. Now here, instead of letting x and y be parameters, the slight distinction is let x, y, and z all be spherical coordinates first, and then plug in what you've solved for. And notice that, again, it just kind of works out. X, Y, and Z are now functions of two parameters. It's just that now they're phi and theta instead of u and v. So it's a little twist, variation on the graph parameterization. This is what I like to call the spherical graph parameterization because it capitalizes on viewing the surface as a spherical graph, in the sense that we have solved for one of these spherical variables. So anyway, I'll say spherical graph parameterization here and there. That's what I'm talking about. Okay. Then you kind of have to think about what's the range of values of phi and theta, you kind of look at the picture and think in spherical coordinates. We've already talked about that a while ago, but to get the upper unit hemisphere, stopping phi at pi over 2 makes it just the upper unit hemisphere. Okay. Real quick comment. My own opinion. This is just an opinion. Let me go back to my picture here. Is that it's just cleaner and more comfortable to use different names for the output variables versus the input variables. So you'll notice here I'm using u and v as my inputs, x, y, z as my outputs. Now a lot of people would make the case, a lot of people do make the following case. Our book does this, by the way. And I'm fine with it. That's not my personal preference. A lot of people would say, well, look, we're eventually going to let u equal to x anyway, so if u is equal to... It's okay. All right, not a problem. It's good to have a little...
It doesn't even vibrate anymore.
Is there... A little comic relief now and then is fine. Yeah. So since u is eventually going to be x anyway, how about instead of calling this u and making up a whole new variable, how about we just call this x in the first place? And how about we just call this y in the first place? And how about we just view this whole, pullback domain, let's just view it as sitting inside of here, inside of the XYZ space. And so the pullback is sort of down into the XY plane. And look, that's fine, right? I mean, X is going to be U, Y is going to be V. That's fine. I just get a little uneasy and uncomfortable because I really like thinking of it as a pullback. And I like thinking of my domain as a different world from my target in thinking about the change of variables function. And it's a lot easier to do that when you give the pullback variable a different name. Right? So that's how I do it. Now, on the other hand, the book will just say, oh, well, Z is the following function of X and Y, and then they just do the algebra from there. And they would then get, at this stage, here, their parameterization would be XYZ equals X, comma, Y, comma, that formula for Z. And you go through all the it's going to give you the same answer. It's fine, I guess, but again, aesthetically, I think it's a little undesirable. So I kind of discourage it. Okay. Okay, that in mind. Now, which of these do y'all like better? A lot of people are going to choose this one. Most people aren't going to choose this one because it's all trig and stuff. Yeah? Would you believe it if I told you that life is much better with this one? Very often. You'd be surprised. Roughly speaking, the reason is because there are these wonderful thing called trig identities. Trig identities, as you go through and do trig algebra, trig identities are going to pop up, and your algebra will just continually simplify in these wonderful ways that are kind of hard to see coming. Not really so much the case with square roots. Square roots are just kind of bad. So I don't want to go through the details here, but I'm just going to point real quick at, how does this go down if you're looking at, let's compute the area of the upper hemisphere. So here's an area scalar surface integral. Area is just add up all the little pieces of area. Our integrand is 1. And our parameterization has these partials, which have that cross product, which has this magnitude, which simplifies a little bit, I suppose. But here's the integral that you end up having to compute. And it's not a very nice integral, really, in the big scheme of things. There's a square root in our integrand, and square roots in our inner bounds, which are going to turn into square roots in our outer integrand. And it's just a life of square roots. It's not that nice. Whereas, if you do it in spherical coordinates, here's your partial derivatives. Yeah, okay, all right, trig, I know. Here's your cross product, and it's like, okay, well, yeah, and you had to use the Pythagorean identity a few times, and that's true, right? But you compute the magnitude, more Pythagorean identities kick in, and check out what your stretching factor turns into, right? And this integral is falling down simple. The bounds are constant. There's no square roots in the bounds. The integrand, okay, it's trig, but it's easy trig, right? It's really nice. So anyway, I'm trying to make a sales pitch here. I want y'all to, don't just look at your options between rectangular coordinates, spherical coordinates, and say, oh, well, rectangular coordinates is easy, therefore I'm going to do rectangular coordinates. No, we have spherical coordinates, among other reasons, because spherical coordinates makes your life easier very often. And having done bazillions of integrals with spherical coordinates in physics classes over a several year period as a physics second major, I'm a big fan, right? And you will be too. Okay. All right. Last real quick observation. I just want to point out that in this special case where you're looking at rectangular graphs, and the book makes a big deal out of this, and that's fine. But if you are looking at a rectangular graph, that is if z is a function of x and y. Side note, it won't always be, right? A full sphere, that's not a graph in rectangular coordinates. It just isn't, right? So not everything is a rectangular graph. Don't hang your hat on this. observation I'm about to make here. But anyway, if it were, and hypothetically, if x is if your surface is a rectangular graph, you're going to use the graph parameterization. The partial derivatives are going to turn out to be this. You can take that cross product. The cross product's going to be that. It just works out really nicely. And this is the formula for the magnitude. So it's kind of convenient, I suppose, to just remember that in that special case of rectangular graphs, there's your stretching factor. And my apologies, I forgot this is a typo. That should be a delta in there. I forgot my delta. But go ahead and memorize that formula too. Right? It's a nice special case. It saves you having to do a couple of steps. But this is only for rectangular graphs. Rectangular. Doesn't work if you're using polar coordinates or spherical coordinates or something like that. Right? And only if it's a graph. And again, not everything is a graph. Right? So your primary formula for understanding scalar surface integrals should be this one. That comes from a parameterization. And secondary special case, to use as every so often it comes up. I mean, surprisingly often actually. But in the special cases where this works out, then know this formula too. All right, and we're out of time. So good place to stop. See y'all later. Have a good Wednesday.